Okay. Hello, everyone. Thank you for joining. I am the host for today's webinar. And before we start with Valerie's presentation, let me quickly briefly give you some insights about IEEE GRSS and the technical committee which we are working towards and the working group as well. So my name is Rajat Shinde, and thank you for taking out time to join today for this interesting webinar. We are hosting these webinar series from all the scientific developments which are happening in AI foundation models, data sets, and everything related to earth science informatics. And so, as we all know, IEEE is one of the biggest society and academic network across globally, and uh, it includes multiple different societies, and one of that is GRSS, which stands for Geosciences Remote Sensing Society. And the GRSS is also spanned across the world. It was founded in 1961. There are almost more than 5,000 members coming from 94 different countries. It has multiple chapters, student chapters, ambassadors all over the world. Um, Majority of you, I'm assuming you are a part of GRSS. And GRSS comprises of all the things which are related to open science and science related to geosciences and Earth observation, which includes publications, conferences, professional activities, education, and technical activities as well. If you want to join GRSS, you can use this QR code or reach out to any of us. I also recommend joining the GRSS e-newsletter to get more insights and regular updates on what is happening in the community. Now, coming to the technical committees, there are a few technical committees under GRSS which heavily work on the technical part of geosciences and Earth observation related domain uh, pertaining to a specific domain. And one of such committee is Earth Science Informatics Committee, which is chaired by Dr. Manil Maski, Iksha, Dr. Sujit Roy, Dr. Gabriel Meoni, and Jerika, who is also in the meeting, is the secretary for the Earth Science Informatics Technical Committee. So, if you want to be a part of it, first of all, you need to join GRSS, and then you can be a part of the ESI Technical Committee. Another way of being a part of it is to subscribe to any of the working group. So there are multiple working groups under ESI Technical Committee. I lead the Digital Twins for Geoscience One, Earth 2 working group along with my colleagues. And if you have any questions or if you are interested in being a part of the working group, please feel free to reach out to me or just say hi in general. I try to reply most of the emails. And yeah, with that, I encourage you all to join ESI Technical Committee and GRSS and get tuned to all these webinars which we are doing. I'll not take further time. I'll stop sharing and will pass it on to our today's guest. So, Valerie, first of all, welcome to the GRSS webinar. And let me quickly introduce Valerie for you all. Valerie Pasquarella is a senior research scientist at Google, and she works on developing foundational geospatial datasets that makes Earth observation imagery more useful and usable to all. Valerie has a background in ecological applications of remote sensing with a specialization in time series analysis. She earned a PhD in geography and MA in environmental remote sensing and GIS and BA in environmental science from Boston University and served as a postdoctoral fellow with the Northeast Climate Adaptation Science Center at the University of Massachusetts Amherst. Prior to joining Google in 2022, Valerie held research faculty appointments at Boston University and Harvard University. So it's great to have you, Valerie. Thank you again for accepting the invitation to present the work. We all are excited about it, and the floor is yours.
All right. Thanks so much, Rashad. So excited to be here to talk to all of you about AlphaEarth Foundations and the Satellite Embedding Dataset. And so let's just jump into it. Given I'm talking to a lot of other folks working in remote sensing, I probably don't have to tell you that we are currently in maybe not just a golden age of Earth observation, but of Earth observation data archives. And so what do I mean by that? In the Earth Engine data catalog alone, we host more than 4 million images from Landsats 8 and 9, not including the legacy missions, 31 million Sentinel-2 L1C products, over 3 million Sentinel-1 GRD products. And as the graph on the right shows, we continue to see more sensors being launched, more data being added over time. So this is really an explosion of data volume. And again, like this doesn't stop. I've got the number down at the bottom. We add about 100,000 new Sentinel-2 images just every week. And so with this massive influx of data and access to these archives of satellite imagery, our challenge becomes not so much the access to the images themselves, but how we translate those images into actionable insights. So the questions we have around, things we make maps of: deforestation, commodity mapping, water resources, agriculture, clean energy use cases. And this usually involves a lot of work where a lot of you sit in understanding how to pre-process these different sensors, these different modalities of images, these different image archives, and then modeling on top of that to then translate those signals that we're extracting from our remote sensing images and applying that to real world problems on the ground. And that's where AlphaEarth Foundations comes in. And so today we're going to talk in a few different steps here. We're going to start with an overview of AlphaEarth Foundations as a virtual satellite that we've built on top of Earth observation data streams. I'll talk a bit more about what I mean there, but here we're really going to dig into some of the details of the model itself. I'm going to give a quick overview of how we evaluated the model to give you a sense of how we thought about assessing its capabilities. And then I'm going to introduce the Satellite Embedding Dataset, which is a new kind of image collection we're hosting in the Earth Engine data catalog that you can build directly on top of today. And at the end, we'll save some time for Q&A. So, AlphaEarth Foundations. As I mentioned, we've got all of these different satellites imaging the Earth, orbiting and collecting repeat observations of the same location. Our goal with AlphaEarth Foundations was to treat this set of acquisitions as a movie from which we could extract a feature space, an embedding space that we can use to characterize every pixel on the surface of the Earth and build this new kind of foundational layer that we can build those different applications on top of. And some fundamental assumptions before we dig into the details here on what we set out to have AlphaEarth Foundations, the model, be able to do. Well, we wanted it to produce embeddings. That is the top line here, is this was a model that was designed not necessarily for fine tuning or for one of the more conventional ways we interact with these sorts of large models, but rather to directly output a useful and usable embedding. And we wanted that embedding to be able to harmonize and summarize. So it needed to flexibly accommodate all of these different data sources and streams. I mentioned just a few in the intro there, but we'll dig in more into all of the different sources that we ended up using and how our architecture was able to accommodate those. We needed to have multiple modalities. And I don't just mean multiple modes of sensing. I mean literally images as a raster modality as well as text. So words as a second modality here that we use to describe the surface of the Earth. We also needed these embeddings to be spatially and temporally precise. So we wanted to say exactly over what period an embedding would apply, not just as a footprint on the ground, but also over a window of time. We needed the embeddings to be small. So we know people working with very classic ML techniques and some of the non-deep learning approaches, you need a feature vector that you can actually manage in a regression or classification workflow. And so we wanted these embeddings to be relatively small in size. And our spoiler alert, our dimensionality is about 64D. So as embeddings goes, this is very compact. We needed the embeddings to be consistent, so we wanted to be able to use them to track things in space and to be globally applicable. We needed them to be semantically meaningful, so they need to capture real concepts. And again, going back to the idea of why are they compact, they needed to be easy to work with and minimize the need for going on and doing even more complicated modeling. Our goal was really to get people working with their label data, their field plots, their on-the-ground measurements, and being able to scale those and get to some interesting questions and insights faster by building on top of the embeddings from AlphaEarth Foundations rather than, say, individual raw image sources. So that's quite a list. And hopefully in the next set of slides, I'll convince you that we built a model that not only does this, but also delivers on our promise to accelerate scientific analysis and the map making process. So high level, for those who may not be as familiar with ML architectures, you can think of AlphaEarth Foundations as a pretty classic encoder-decoder type structure. So we've got images coming in. Those are being encoded into a latent representation or our embedding space. And then what we do is we then give the model a date time, a time code, and we say, hey, model, take one of your little decoders and decode into a different image source. And those targets, as we call them, can be anything from held out images from our input streams or entirely different data sources that allows us to then encode that information into the model weights. And so pretty simplistic view of what's generally going on, but the point really being that the latent representation, the embedding that we're after, sits between this data stream coming in and then our tasks that we're decoding on the output side. So like I said, very simple representation in the first slide. This is the figure from our paper, our preprint, which is up on arXiv, and I strongly encourage you to go and dig into all of the details there. But we've got that same general structure represented here in this diagram, and I'm going to walk us through some of the key pieces to hopefully ground you in what's actually going on inside the AlphaEarth Foundation models. So let's start with that first part, the encoding. So in my first diagram, you saw all of the Sentinel-1, Sentinel-2 images coming in. Here it's that column all the way to the left, where you see we've got individually time-stamped images. This is very important that they all have precise timing and we treat them like a video. So we respect their sequencing coming in. And so our pre-processing blocks handle each of our primary image sources separately. We've got a couple of steps where those sources are processed into features. We then stack that giant feature vector together with that little green bar. We're missing the arrow right now, but that represents the time codes associated with those images and their features. And we pass them through this dotted line center section that says STP blocks. What are STP blocks? These are where most of our model weights go. And STP stands for space-time precision. Walking through it in backwards order with the other diagram on the right here, space is how we handle our spatial dependencies. And so when the model is given a input image, it is able to attend to an entire image chip. And in this case, our image chips are 1.28 by 1.28 kilometers on a side. So the model is able to account for long distance relationships using the spatial pathway and looking across this entire sampled image chip. Time is handled in a similar way, except now instead of being able to attend to the entire image chip, we're going to be able to attend to other images in our time series. And because we're respecting the ordering of our images, we're able to start to look for things like, imagine phenology playing a role and seasonal phenomenon like snow cover coming and going. The model is able to look back through the history of images and use the temporal context when it's creating the embedding output. And finally, you might wonder, what's the difference between space and precision? Well, space is the long-term relationships. Precision is how we get that very crisp local detail. So this is a convolutional pathway where we actually use a little tiny window over each 10-meter pixel in our output to understand not just those long-term relationships, but really that localized context that's contributing to our different signals. And so very abstracted in the diagram here, lots more details in the paper, but the big takeaway is that the model is able to cross-combine these relationships from its spatial context, temporal context, and as we'll get into more, all of the different measurement spaces that it's being asked to translate between. And so another important piece of the diagram that goes just before where we create the actual embedding vector here is what we call our summarizer. So now we're out of our STP blocks and we're headed into now a featureized version where we've done all of that cross combining of the different dimensions and axes. And we've still got our time codes, but we don't have a single summary. What we have is this very long vector of the output features. And what we want is similar similar to how we would make a composite and we set a compositing period, we want the embedding to represent a specific period. So we give what we call the summarizer piece of the architecture a valid period, a period over which we want it to summarize observations. So we give a time start and a time end. And what we get out of that is an embedding that translates all of those features from all of the images that it's seen into an embedding that summarizes that specific period. So I've already touched on from our laundry list of things we wanted the model to do. Here's how we've gotten some of our temporal precision as well as our spatial precision. And that little red, yellow, and blue square is the embedding. That is the thing that we are surfacing in our satellite embedding data set. It is the goal of the model to produce a high quality embedding vector. But you might be wondering, okay, how do you get that then, right? We've only seen what's coming in. How do we actually learn to make a good embedding? And that's where the end stage of this diagram comes in. So reconstruction is one of the main tasks we use for learning. I alluded to it in the earlier slide where I talked about decoding. Here's a much more detailed view of our actual decoding process. We are able to take that embedding vector, we sample it using a von Mises-Fisher distribution where we're able to sample uncertainty on this 64-dimensional hypersphere that the embeddings live on, if you want to think of it that way. And we take those sampled embeddings with some uncertainties and we use them to reconstruct different image targets. And so on the right here, we're seeing reconstructions of Jedi, which is not included in our input sources, but it's something we're asking the model to take that embedding and reproduce a Jedi image, wall to wall. We know Jedi's only got footprints in the middle, but let's create a Jedi image and we'll compare that to where we actually have Jedi measurements as a way to learn if our embedding is able to characterize that information. Similarly, I've got a Sentinel-1 image, so models reproducing images it hasn't seen in training. These are images that were excluded from the input stream. And then finally, some semantic information. We used NLCD as one of our very weak constraints on reconstruction to put in a bit of that semantic information, because as I mentioned, one of the goals was to make sure there was some semantic meaning and that the embedding space could be used to map to real world on the ground conditions. But it's not just those three sources. Let's get more into the full measurement space here just for everyone's context. So we've again used our input data to then reconstruct our output data, and what's sitting in the middle is this embedding that has to encompass information from the input sources that can be used to reconstruct its target sources. Therefore, we know that the embedding has that information encoded in it and in the model weights. And our full list of data sources is here on the left. I've already mentioned the three big ones, Sentinel-2, Landsat, and Sentinel-1. We also use ALO's pulsar data so that we have L-band in addition to the C-band SAR. This is all on the target side of those reconstructions. So we're not seeing these in the input side of training, just on the reconstruction. We have elevation data from the Copernicus DEM to tell us about topography. We've got that Jedi LiDAR returns. So we actually use the full set of relative height metrics as a distribution here to learn from. We've got climate variables coming in from ERA5 land, including precipitation, air temperature, and surface pressure, as well as dew point temperature. We've got gravity field data for those interested in subsurface and water availability. We've got the equivalent liquid water thickness out of GRACE. And as I mentioned, we've got some weak constraints on semantic information. So the National Land Cover data set is one that we used for reconstruction. We also added the USDA cropland data layer for historic years as an additional target in a recomputation of some of our embeddings prior to the release of the data set. And then to the point about additional modalities, we actually have two different text data sets that come into play. So we have text that is associated with Wikipedia articles, so geocoded article locations and the text that goes with that. We also took observations out of the GBIF data set, so biodiversity observations, and we attached to those text embeddings from the articles associated with the species for each observation. So if you have a species observation, we took the Wikipedia article associated with that species and got a text embedding for that. And I'll show you in a moment where that comes into the process, but big take home, we had a lot of different data sources. And in terms of representation, these data sources were sampled for a total of 5 million sites distributed globally. We stratified by ecoregion and kind of where we had the available text information, which, as we know, tends to be concentrated more in populated, well-described areas. So we have those 5 million sites. We collected a total of 10 million video sequences. So for each site, we would pull a year-long sequence of all of the sensor data and other sources, giving us a total of 10 million videos that we're training on. And the big number at the end was we sampled about 3 billion individual image chips. These are those 1.28 by 1.28 kilometer chips. And that is what went into our pre-training. So I already talked a bit about our reconstruction process. So being able to reconstruct the embeddings as, or reconstruct targets as a way to learn a embedding that is representative across those different data sources. I want to briefly mention for the folks interested on the modeling side here, the 3 other objectives that really are at play when we were training the model, because these are really important to how those embeddings are structured and how we make sure that they're really usable for the sorts of mapping use cases that we want them to be usable for. And so our batch uniformity objective, we use this to pair a shifted version of our input data batch. So we take a element from a sample, so one of those video clips, we pair it with a different sample, so offset by 1 in the same batch, and we optimize that the embedding has to be learned such that we are minimizing the dot product between the 2 embeddings. We'll talk more about dot products later in this talk, but the idea is we want the embeddings to be perpendicular to each other for different batch elements. This also has the nice property of making sure that our embeddings are in a standard range, and the fall off the outcome is that they're well distributed over this unit sphere. So our embeddings are covering the surface of our feature space in 64 dimensions. It's a little hard to think about, but bear with me. For the contrastive consistency objective, so batch uniformity is giving us kind of that uniform distribution and normal range. Contrastive consistency is making sure that we're robust to the reality of working with remote sensing data, which is where we expect that sensors may drop out, we may be missing inputs, we may have gaps in coverage, irregularities. And so contrastive consistency is actually a student-teacher model setup where the student is given a subset of possible images. And it's being encouraged to create an embedding that looks like that from a teacher model, which has full information, despite the fact that the student had much less information going in. So by doing this, this allows us to make sure that if we lose a Sentinel-1, as was the reality with the Sentinel-1 coverage for the last year or so, we're able to still generate a consistent embedding, even if we don't have one of our core inputs. And then our final pathway, our final objective that I mentioned earlier, are text objectives. So I said we were generating embeddings for Wikipedia articles and attaching them to article locations and species observations. Our text contrastive objective is similar to the student teacher with contrastive consistency. Text contrastive is we are aligning our Earth observation embeddings with the embeddings that are frozen out of these text encoders. So we've generated a text embedding for the article context, and we're asking the model to say, take that Earth observation embedding, the AlphaEarth Foundations output, and make sure that it is aligned with the text embedding so that we're able to pull in some of the semantic information there. And it's the combination of all of these embedding objectives that help us build a feature space that we believe is really useful for the sorts of things we want to use it for. And if you take nothing else away from this section on modeling, the big take home is that you can think of AlphaEarth Foundations as a virtual satellite that's capable of imaging any place over any time period. So I hesitate to say it, but it's sort of like a fancy AI powered composite where we're taking all of these different data streams. Rather than synthesizing each one independently, we're generating a unified feature space from all of these non-uniformly sampled records, and then we are able to summarize that harmonized data record for a given, we call it a valid period or a summary period, but anything from a day to a month to an entire year, you can then take the harmonized record and generate that summary that still respects things like temporal trajectories and all of the spatial and measurement context. So we have this continuous record that we're able to sample from. And it's this record that we sampled to create what we call embedding fields. So for each of our outputs is a 10-meter pixel, but we can generate those as a continuous layer covering the surface of the Earth. And if you then take these in an image format, what this really looks like is an image where each band corresponds to an axis in our embedding vectors, in our embedding space. And so you'll notice in our data products, we name them A instead of B because these aren't like classic bands. These are actually the coordinates of the 64-dimensional embedding vector that's being output of the model. We just surface them as bands because they're spatially continuous and it's convenient to put them in an image format like any other satellite image would be hosted. So I'll get a bit more into actually working with the embedding vectors in a second, but before we dive into that, I'm sure the scientific audience here must be asking yourself, okay, but how did you know that the model was going to perform well? How did you know that it was ready to go out into the world? And for this, we had a set of evaluation data sets. We developed this set ourselves from 10 primary sources that we translated into 15 individual data sets. And these were all selected to represent real world applications. So if you look at the list of data set types and names on the right there, we're really trying to mix different domains, everything from land cover and land use, crop type mapping, tree species, getting into more species distribution, things like evapotranspiration, surface emissivity, so those biophysical properties. And we wanted to make sure that we were representing those diverse use cases that we often see people using moderate resolution imagery for, that they were in our evaluation set. We also tested the kind of primary modes of analysis for remote sensing. So these data sets represent types of classification with different numbers of classes. Some of them have multiple hierarchies, which is how we got more than one data set out of a single source in most cases. We also have, again, those biophysical variables are regression problems, so being able to handle continuous outputs. And we looked at some change detection use cases as well, testing that idea of could you use embeddings with enough temporal consistency to be able to find changes through time. And the coverage of our embedding, our evaluation data set, the individual data sets vary, but we do have generally global coverage because we've sampled across all of these different data sets and use kind of best available, biggest scale possible. I'll also call your attention to the temporal cadence. We evaluated not only annual summaries, but single date and monthly as well, depending on when the records in the eval data set were available for. And the final really important thing, and the thing that's going to carry through into some of the examples I show later, is this field I've circled that says max trial size. So we really wanted to make sure that the embeddings were going to work when you didn't have a massive amount of data. We wanted to know what performance looked like when you only had a few hundred or a few thousand examples per class. And so we capped our maximum numbers of observations from an individual class or bin in the case of regression to the max trial size shown in the column there. So we never have more than 300 points per class or points per bin, and sometimes as few as about 50 for one of our crop data sets. And again, this is to proxy the real experience of if you're starting a project from scratch and you need training data, we wanted to make sure that the embeddings were going to perform well in that low data regime, not just in the wealth of data scenario that everyone ideally would like to have. In the interest of time, I don't want to dig too much into all of this, but for our comparisons, we did have a set of baselines that we were comparing the embeddings generated by AlphaEarth Foundations against. These included a set of controls, so XY and XYZ, so simple proxies for location. Can we do just as well if we're just predicting based on where the location of things were? We used a kind of basic vision transformer, not even trained on remote sensing data, to say, is it really just the deep learning and we really just need a lot of parameters, and we could do just as well with something trained on camera imagery and transfer it. Some classic remote sensing feature spaces, so composites, CCDC as a representation of harmonic spectral temporal features, almost think of it as a design temporal embedding, and mosaics, which is a engineered embedding space that uses different sized kernels in order to generate embedding outputs, and then a handful of other foundational models or models that were developed, again, specifically for Earth observation data, in contrast to that vision transformer that was more for camera imagery. These are models that have come out in the community as being specific to Earth observation applications. And what we found across the board is that the AlphaEarth Foundation embeddings, when compared with the embedding equivalents out of these different approaches, improved across the board performance on all of our evaluations. And what you're seeing here is the magnitude of improvement, so the number of times improvement over the next best model, which is listed on each bar. The numbers actually represent the balanced kappa adjusted accuracy, so as conservative as possible here, with the AlphaEarth Foundation's evaluation score on the top and the score from the next best model on the bottom, either reported balanced accuracy, or I believe this is an MAE for the R squared for the regression evals. But really the big take home for us in our evaluation stage was that we were achieving performance not just on one or two tasks, but across this full diverse set of tasks, time periods, locations, that the model was consistently outperforming the other options, and that there really wasn't a clear second best. Other models exceeded on different tasks, but we were consistently able to perform well across all of them. I like to show our evals again to give you a sense of how we were thinking about evaluating, but the really important thing is that it wasn't just about the numbers that we saw on this figure, but we really wanted to make sure that the embeddings performed well in actual real world user workflows. And that was just as important, if not more important, than the benchmarking tasks themselves. And that's where the satellite embedding dataset comes in. And this is something I'm very excited to talk to you about because it's something that you can all go after this call and try yourself if you haven't already. So what is the satellite embedding dataset? It is a new image collection in the Earth Engine data catalog of annual summaries generated by AlphaEarth Foundations. What do I mean by that? Well, these are those embedding vectors. Told you we surface them as imagery, and we put them into an image collection so that you can work with them just like you would any other image or image composite in a remote sensing powered workflow. And it's as easy as, if you're an Earth Engine user, accessing EE image collection, Google satellite embedding V1 annual. And these are annual summaries. So that summary period that I mentioned is a calendar year here, and we have them available for the years 2017 through 2024. And we will be generating a 2025 layer as soon as we're through the end of the calendar year and we get all of the ingested images from 2025. We'll be working on generating that next layer. But this is an image collection. Just to show you a little bit about what that looks like. So I mentioned that the model generates an embedding field, or this continuous surface of embeddings. Well, it's nice to have wall-to-wall coverage, but working with that in practice is not always as practical. And so our embeddings are actually hosted as tiles. So you can achieve wall-to-wall coverage by mosaicing them together, but they are tiled in the collection itself. And each of those tiles consists of 10-meter pixels, and each of those pixels is then associated with one of those 64-dimensional embedding vectors output by the model. model. And so it kind of looks like this. And another nice thing to call out while we're talking about image collection, if you're an Earth Engine user, Earth Engine is built on the concept of pyramiding, so being able to zoom in and out and aggregates at different levels, while the embeddings were, as part of the encoding process, designed to also be linearly separable, which means when you start to pyramid them, you can mean up and aggregate to coarser scales, and they should still retain semantic meaning and meaningful distance relationships, which is all just to say that the embedding collection, the satellite embeddings in Earth Engine are designed to work well in Earth Engine's architecture, as well as any sort of distributed, piled, pyramided based architecture, and just kind of plug and play there. So that was a lot on the data set structure and the model that sits behind it. But for those of you who maybe like myself are more interested in the what do you actually do with this? So it's really cool that we were able to build this collection. What are you going to walk away and maybe try? And the kind of common things I talked about from our evals: classification, regression, and change detection tasks. We want you to be able to make good maps with less training data, scale biophysical measurement, and track changes through time. We also have this fun category called similarity search, and you may not have seen this before. This is something that is more common in embedding-based approaches and some the computer vision side of things, but this is the idea of using embedding vectors to find similar places. And let's start with a really quick example of this, since I think it's a very powerful tool and just generates some really interesting insights into what's captured in that embedding space with pretty low effort. So similarity search. I said when we were talking about batch consistency, something about dot product. This is a bit more of an explainer on what is a dot product. If you're thinking back to your math classes way back when, might not be a term you've heard for a while, but a dot product is a way that we can compare two different vectors. So when we're dealing in band space, we often do things like subtract to look for differences. Here, we're not operating in band space, we're operating in vector space. And so dot product is a way to collapse the magnitude and angle between two embedding vectors into a single scalar value that represents the similarity between those two vectors. And in our case, our vectors are unit length. So they're all distributed on this 64D unit sphere. So the unit length means they're all magnitude 1. So really what we're looking here is just the cosine of the angle between the vectors. In data science, this is often called cosine similarity. Again, in our case, it is actually the dot product as well. And what this is going to tell us is if we take the two embedding vectors, multiply them together, and take the sum over the products, this gives us a score on the scale of -1 to 1, where values that are closer to -1 are more different, so closer to 180 degrees apart. Values closer to 0 are 90 degrees. So remember, we are using it as a target for optimization. We want to get things close to 0. That means they're perpendicular. And when things are very similar, they should be close to 1. And great to see it in the math, but I'm sure you're wondering, so what does this really look like in practice? Well, let's take this example in the Mekong Delta in Vietnam. And I've got that little white box there that's over some of the mangroves right on the fringe of that delta. And so these are mangrove trees in the delta kind of Channel Island. And what happens if we take a pixel in that white square? So that little black dot here is the center point, and we compute the dot product between the vector at that point and all of the other vectors in our viewshed here. So what you're seeing in this map is that dot product similarity. So places that are lit up in the brighter, whiter tones are places where those vectors are very closely aligned. Their dot products are very close to 1. Versus as we get into those more orangey tones, we're moving further apart. And then when we've got the darker purples and closer to black tones, we're seeing much more dissimilar. So we can see here, we've almost got a map of what I would highly suspect are other mangrove places in the Mekong, just from a single, very simple calculation of the vector similarity. And cool, like that's working well in this very localized example, but does it stand the test of space? Well, let's zoom over to literally the other side of the world, to Belize City and Turnip Atoll. And there are mangroves in the ecosystems here. What happens if we take our same clicked points from over in the Mekong Delta and we generate that same similarity score for every pixel in this place? Well, there we go. So maybe not quite as dramatic, some of the forest differences, but those mangrove areas, the stuff that's right along the coast, despite seeing a whole wall of green in the high-res image, we're now seeing places that look more like mangroves in the Mekong, and I would venture a guess are more likely to be mangroves in this area as well. So we generalize across space, and it's really quick to calculate this. Again, really simple way to start exploring embeddings. I'll give you one more example because n of 2 is still pretty tiny. What if we had a third case where there are definitely mangroves in the Florida Everglades? Here's that high-res base map for comparison. And if we look at the similarity and embedding space to our mangrove example, here we go again. We can see these are likely mangrove areas, mangrove forests in the Everglades. And this is so impressive to me because this is really just one point and similarity, almost like sort of the simplicity of an NDVI calculation, really simple band math, but we're able to get this very powerful tool for looking to match like examples with other like examples. And for those who are like, well, you're showing vegetation, mangroves. I don't work in vegetated environments. Just as another data point to consider, here is a similarity search, not for vegetation, but for a biosphere reserve in the Sonoran Desert in Mexico, which is actually a volcanic outcropping. And so our clicked point here is somewhere within that kind of bright spot in the center panel. And you can see this biosphere reserve is fairly unique, even in the broader context. If we go all the way to the right-hand view where I've zoomed out a bit, you can see where it's situated in Mexico and that it's really lit up as a distinct land surface type there. And then if we look for our analogous examples, one of the other bright spots in the world is another volcanic field, this one in Libya. So we are finding that we're able to pick up on those geologic similarities, those surface similarities, not just vegetation properties. And so again, similarity search, super powerful way of interacting with embeddings. For those who show me the code. Here is in code the example that I just showed you here, where we are sampling an individual embedding point and applying that comparison to every other vector in the image. There is a code snippet for that, and I can share links in chat afterwards. But this link up at the top, goo.gle/satellite embedding similarity demo, is a nice app where you can do exactly what I was doing in those examples and click your own points for different years and generate similarity layers on the fly to start exploring and playing with the embedding space for yourself. So don't just take my word for it. Go try it. And we're always curious what people find and learn as they're trying to look for these similarities in the embedding space. And I should also call out, we do have a tutorial on this in our dev site tutorials as well. And so this tutorial covers some extensions of the similarity search. If you want to use multiple points, resample to different resolutions, you definitely check out on the Earth Engine developer page. The similarity search tutorial walks you through this in a whole lot more detail. So I know I want to leave time for questions. So I'm going to run through the rest fairly quickly here, but as our next example, let's do a quick dive into how you would use embeddings for change detection. So we just talked about dot product similarity within a given layer. So looking at a sampled point and other vectors kind of in the same year, if you want to think of them in the context of the annual embeddings. What happens if we want to do the same thing, but through time? It's actually even easier. So where the other code involved sampling, this is the full example. If you go to the catalog page for the satellite embedding data set, you can just run this yourself right now if you have an Earth Engine account. But essentially what it's doing is it's taking the embedding collection, filtering for 2 different years. So we got image 1 is our 2023 embeddings, image 2 is our 2024 embeddings. We multiply those 2 images and then reduce to get the sum. And that is our dot product, not through space, but through time. So it's going to tell us how similar was a pixel between those two different years. And let's look at an example of this in the Central Valley in California. So if you're not familiar, this is a lot of agriculture. We've got down in the valley. We've also got the mountains to the right. And so here we see patterns from forest fires, changes due to timber harvesting. California also a lot of water resource monitoring. And so we see these reservoirs where we can look at the actual amount of water through time. As I said, Central Valley is a big agricultural area, so we can actually look at fields within the valley and how those are shifting year to year, and of course, interest in human modifications, so how suburban development is characterized in the embedding space. And before I jump into the dot product, let me just quickly show you. So here is an RGB view of the embeddings. They're beautiful. I actually love looking at embeddings in these 3-channel composites, but the downside is there are only 3 channels. So here we are just looking at 3 axes of that 64-dimensional embedding space. And if I flip back and forth between, here's the embeddings for 2024 versus a few years back in 2020, and we go in between, we can see that even just in these 3 axes, we're seeing some distinct changes. We can see changes in water level. We're seeing some of the impacts of a fire that was in that forest fire area, as well as changes in what's going on in the agricultural fields. And down at the bottom, we can see that kind of green stuff lighting up is a development that's going in at the fringe of, I believe that's Sacramento down there. And so all of these different changes manifesting in just 3 dimensions of the 64-dimensional embedding space. The dot product is how we're going to get to looking at the full embedding vector and how that varies through time. And when we make a dot product map, we get something that looks like this. And so here you can see up in the green box there, that forest fire example, places where the fire burned through and cleared out vegetation, we see a large deviation, so bright colors. But there's these little dark spots. Those are places that had previously been harvested. And so they were already clear. And we can even capture, because of that spatial precision, that 10-meter detail, that we're able to distinguish those little patches of harvest as relatively stable in terms of they were already bare versus the burned area around them. I love looking at the change in the reservoir for a similar reason. We've got that area of channel that even during one of the years, I can't remember if it was 2020 or 2024, is a drought year. So the reservoir was very low in one year and much higher the other. That black area is what stayed stable between the 2 compared years, whereas the white, brighter areas are where we saw more of a difference between the embedding vector, more fluctuation in the signal there. For agricultural monitoring, we can see some of the fields are staying relatively dark. They haven't changed very much, where others are much brighter. We see a lot of change in agriculture. That's because the embeddings are capturing that temporal trajectory. So we've got a whole year of imagery. If you change the crop type, the timing of harvest, the planting time, we would expect to see a difference in the trajectory. And if you expect to see a difference in the trajectory, you'll likely see a difference in the embedding as well, with brighter colors indicating bigger differences. And then finally, down at the bottom, we're seeing some of that suburban development, those areas that were showing up as green, but we're also picking up on changes in fields nearby, which does highlight one of the downsides of this, which is it is not a supervised approach. This is just unsupervised change detection and embedding space, and there's so much more that you could think about doing once you have some label data and really refining a process. But as that first cut of, is there a disturbance? Has something changed? Embeddings are super powerful. All right, so we've covered similarity searches. We've looked at how we can do dot products in space versus time with change detection. What happens if you don't want to just try these kind of basic unsupervised approaches? What if you do have label data, and how do embeddings perform for those classification and regression tasks? And I'm going to go through just a handful of examples here to show potential, although I'm sure everyone who curates their own data sets can build much more powerful examples than these. But these examples, I'm just going to take a couple of data sets that were used in our evaluations that I mentioned earlier, specifically the LCMAP reference data set, which was used to produce the USGS LCMAP data sets for the US, and a data set called Glance, which is used to generate a global land cover map. So different classification legends, different coverage in terms of what's being sampled for those data sets, but that same general concept of land cover. And we're going to look at an example. I'm based out of New York, so we're going to look at Manhattan and surround, just to give us a taste of what this looks like when you use embeddings to actually make a map, not just generate statistics. So the first example I'm showing here is if you actually just take the 300 points per class that we used in our evaluation data sets for the LC map legend, which is shown on the right. And I've got up at the top kind of the distribution of the training points there, so you can see we've got a relatively well-distributed sample over the United States. We can see we're picking up pretty clearly on the impervious areas here in the city, plus some of the forest and croplands kind of out in the larger metro area. And another thing to note in this map is it's actually a blended random forest probability. So unlike our evaluation trials, which I'll show you in a second, where we used KNN and linear classifiers, the map example here is using a random forest, 200 trees. Again, there's 300 points per class. We got something that looks like this, which is pretty good for 300 points per class. And I will say, if we compare this to our low shot comparisons, where we're using k-nearest neighbors with a neighbor of 1, neighbor of 3, and then linear classifiers, we were able to achieve a balanced accuracy of over 0.8 on this data set, which is greater than the other methods that we compared to. But again, this is that sparse data scenario where we're kind of at the lowest possible number of samples, the most extreme kind of rare situation that we tested. But what does this look like if you actually use all of the points? So the second map is showing the same legend, same classifier setup, except this should say instead of 300 points per class, this is actually all points per class. And so we've got a much greater number. It's actually the combined set of train and test here. And we get quite a bit of improvement by adding additional sample points here. We can see a lot of herbaceous areas that weren't really showing up in the original map start to show up when we add more data, which is just to say, if you have more data, you can always do better by including more labels. But in that low shot scenario that we tested for, you can already start to see really clear patterns in land cover where you might have needed, thousands of points to train a random forest and like raw imagery inputs like composites or harmonics. Again, moving quickly, same setup here. If we look at the Glance data set, which is that global data set, and we do the 300 points per class, got a lot more classes here. What strikes me in this example is if we flip between, and I should call out that in terms of low shot performance, this was about a 0.6 balanced accuracy, and again, exceeded the other baselines. But if we compare the 300 points per class version to the full version here, and I flip back and forth, we see less of a big change in distribution the way we saw in the LCMAP data set, and more of an increase in confidence. So again, this map is showing kind of the probabilistic view of the classifier outputs where they're blended based on the top one probabilities, and we can see that we get a lot more clarity in especially the vegetated areas. So that global sample, depending on the quality of your points and the representativeness, we actually have a more stable output, and the difference isn't quite as dramatic here between having 300 points and 30,000 points, 300 points per class, and then 30,000 points total. So again, really quick examples just to show what we were trying with some of our data sets, and we're always curious to hear how this works in practice for folks, especially when you're working in those really data limited regimes. One last proof of concept. So if we look at Singapore here, that Glance data set, we can take what we trained, over in the US example, and we're looking at that same random forest applied to Singapore, and can quickly generate a land cover map for anywhere in the world. Last few before we get to Q&A, just showing it's not just land cover. We did some experiments with the samples from the USDA NAS cropland data layer, not the one we used in our training, but a newer version that was produced with different methods. Here you can see a side-by-side, 150 points per class. I believe there's 87 classes total that we ended up aggregating to, and they're color-coded into fewer bins shown in the legend here. But the big take-home being that with just 150 points per class, We can see very cohesive spatial patterns. We can see fine scale details, kind of the edges of those center pivot fields, and all with very little label data. And to drive it home, again, not just our own evaluations, what we've tried, we've been very excited to see the USDA has actually produced a new Hawaii cropland data layer built on top of the satellite embedding data set. They were able to generate a 10-meter map of Hawaiian crops for the first time by using the satellite embedding data set and training classifiers, applying them at scale, and they now have 2023 and 2024 crop maps available. If you see the press release, they've got a really nice tool you can go and actually look at the data layers. So working in practice, not just in the lab. And to drive that home even further, we've been tracking a lot of preprints and other papers coming out that are using the embeddings. We've seen people report improvements on urban air quality predictions in Quito, Ecuador, groundwater fluoride predictions for water management with predictive power improving across other models tested, and going back to agriculture, not just crop types, but folks trying to predict corn and soybean yields. And getting results that were competitive with more complex processes. So we feel fairly convinced that the embeddings are working, again, in practice for these different use cases that we tested for, but we will leave all of you to be the judge. And with that, quick summary, AlphaEarth Foundations, the whole design was to generate embeddings and to function as this virtual satellite that's able to image the Earth's surface over space and time. We're looking to learn meaningful patterns, not just through space and time, but also across data streams and be able to generate those spatially and temporally precise embedding vectors. All of these outputs, the satellite embedding data set, how we built the embedding model, were designed for practitioners. So they were designed for people who might normally reach for a composite or a raw image source, but being able to put the power of not just a single sensor, not just a single modality, but all of that goodness learned from a big deep learning model into this compact representation that can supercharge all of the insights and scientific analysis. And with that, we think of our embedding images are this new foundation, AlphaEarth Foundations, a new foundation on which many different Earth observation applications can be built. And if you're looking to learn more, I can leave the links up here, but we've got some blog posts, our paper up on archive, the data catalog page coming soon to cloud as well. If you're a GCS user and want to get away from the Earth Engine catalog, we'll have some options there for you very, very soon. We have a tutorial series where you can actually try some of these applications and deeper dive into things I've just touched on today. And if you're still a little lost, what the heck's an embedding? Why should I care? I like to point people to that link at the bottom, which is a great blog post from Google Cloud explaining not remote sensing embeddings, but text and image embeddings instead. And with that, I can stop and thank you all for listening.
That was awesome. Thank you, Valerie. Great presentation. Let's jump right into the questions. I see a lot of questions. How do you want to do it? You can look into the Q&A panel already. And so first question is, thank you for the nice presentation. Do you have any plans to release with higher temporal resolution, that is on a daily or monthly scale?
Yeah, so we are actively exploring what it would look like to work at those finer temporal cadences. We're currently working on a small pilot where we're testing generating embeddings for smaller scales, and we're also trying to understand what people really want to do with the finer temporal resolution. Between questions, I'll see if I can get a link in the chat, but in the Earth Engine data catalog requests, for those who are familiar, if you go to where you can request a data set, we have an open request for subannual embeddings. And the more people who can add their use cases and help us understand, do you want monthly embeddings? Do you want quarterly embeddings? Do you want weekly embeddings? What we're really looking to see is how many people want different flavors. Do you need something super custom? And that'll help us understand, how we might want to surface those sorts of capabilities in the future, how you might either another data set or being able to order something more custom. So we are very much in active learning from the community mode, and would appreciate anyone who wants to weigh in on that bug and register a use case. That really helps us understand what would help people the most.
Awesome. Uh, Next question is, why are so many data sources only used as a target and not as a source?
Oh, it's an excellent question. So we tried to pick a set of like relatively consistent, strong historic coverage flagship sensors to be our inputs, because we need those input sources when we run inference. We then treated our target sources as data sets, like for example, with JEDI, we don't have wall-to-wall coverage. It's very difficult to use that as a source, but by using it as a target, we can still encode that information into the model weights. So we're able to learn from that information, but not require it at inference time. And in some cases, like I believe for Grace and for Pulsar, we actually tested both to see, and we often found that putting things on the target side was either equivalent or better performing than piling on more on the input side. So very much towards that, we wanted to be able to produce these operationally. We wanted to be very thoughtful about where we were incorporating different types of signals and different limitations of the actual observation strategies. And so we ended up with a lot of data sources that we want the information from, but we don't want to be dependent on them for inference. And so they end up as targets instead of sources.
Interesting. That's very nice. And I think building on that, there is another question which is like, how was missing data and differences in resolution taken care of? How come static and dynamic variables treated on equal footing? And this is something which I also wanted to ask uh, at the harmonization level, because that's a problem which we face across in the earth science domain a lot of times when we are doing the research. So if you can provide some insights on harmonization part.
Yeah, so I would have to consult with the engineering team on the specific details here. If I remember correctly, we got everything resampled to 10 meters in order to be consistent on the input side, but things are sampled bilinearly, so we're able to preserve kind of those pixel to pixel relationships and not have those like hard pixel artifacts. I think the more interesting thing to talk about is how we handle missing data and bad data. So one question we get a lot is, how do you deal with clouds? So people might be surprised to hear that what goes in on the input side never touches a mask. So the inputs are all given in their full form, no surface reflectance correction, all L1C products for the optical data and kind of the raw DRD for the Sentinel-1. And where masking comes in is on the reconstruction side. So when we go to reconstruct, say, an optical target, an unseen Sentinel-2 image, we actually apply a mask there. And so the model is only incentivized to reproduce the signal for the quote unquote good pixels. And that way, we're not learning any additional noise in our bottleneck. And given the number of examples that we have and the number of sources we're learning across, and the size of that bottleneck, which is very tiny to begin with, we're able to effectively get to more of the ground-based signals by only reconstructing and computing our losses against quality observation. And that extends not to just cloud cover. We apply it for the radar data sets. There's lots of quality flags and masking there. And we incorporate towards the harmonization and data handling side, also the other sensor metadata at reconstruction time. So another one that usually comes up in how we handle things is like, difference in ascending versus descending for Sentinel-1. All of that information never touches our bottleneck. It's part of the reconstruction task. So when we ask the model to reconstruct something, we say, here's the image, only the good pixels. Here's the date you need to reconstruct. Here's a bunch of sensor metadata for this that'll help you do a better job. Go forth and reconstruct, and we hopefully minimize the loss that way, but we don't encode things like the sensor nuances and that like noise due to QA in the embedding itself. So some very clever ways to handle masking, missing data, and where we want things encoded versus where we want the bottleneck to be more pure information content and not those sensor minutia that often we get tripped up on trying to harmonize and standardize across these very diverse data sources.
Yeah, awesome. So while we are talking about doing the prediction, can the model be adapted to predict measurements from new sensors?
From new sensors. Yes, though any additional prediction, we'd have to end up going back and retraining and incorporating those into the, like if you're adding a new sensor, the weights are going to change. So the model is as it stands now. The architecture could presumably take in new sensors, but we also did think very hard about representing different measurement spaces. So it wasn't just an exercise in how many different sources we could cover, but more how many distinct types of information. And we wanted to make sure, like you saw with the radar instruments, like trying pulsar in addition to Sentinel-1, or folding in, different resolutions of optical data. To be honest, Landsat is very much on the input side, not just for the optical, but also the thermal information and panchromatic. And so we tried to be very diverse in our past to begin with, so that we were learning across those distinct spaces, not just lots of redundant additional sensors.
Got it. We are getting a lot of questions, so I'm picking up on my own. There is one question which we got a lot from accessibility point of view. So, are there any plans to extend accessibility of Alpha Earth beyond Earth Engine, specifically using Python environments, which also goes to the satellite embedding dataset, as well as other codes available? The fine-tuning codes or the PyTorch codes are available for the AlphaEarth Foundation models. Uh,
Yeah, so we've gotten this a lot. We are working on, and please stay tuned to various sources. We'll be getting the word out. We are making a copy of the data set available just in cloud storage for folks who want to work with the data set directly and not necessarily deal with or work with the image collection in Earth Engine. There will soon be a bucket available with the same imagery, but hopefully that helps with interoperability, folks who'd like to download locally, and you don't have to go through Earth Engine. That said, hopefully it's still very easy to use in Earth Engine, and definitely pros and cons kind of to both sides. In terms of the model, we currently have no plans to make the model itself available. If you've run a foundation model or any Earth observation workflow, you know the pipeline is one of the hardest parts of this process. And so what I was mentioning before about our explorations into subannual is very much in line with that. We're looking for ways that we can surface the model capabilities to folks without having to necessarily ask you all to run the massive pipeline that it takes to process those video clips and turn them into meaningful embeddings. So let us know again if there's preferences on the subannual embeddings and how you'd want to access, but for the time being, yeah, nothing on surfacing the model itself.
Awesome. Thank you. Looking forward to it. And then there's another question which is related to the multimodal part. So as you said, there is text data which is going in as the input. And there's a question related to it which says that, can you give us a sense of how much text that is being used as captions was available for the video or chips at a global scale? Specifically, although there is a lot of Wikipedia text available, it sounds challenging to connect it to global scale or image and video chips. So that is explicitly descriptive of the image or video chips. So some insights on that aspect would be great.
Yeah, that is a great question. We got a lot of questions about the text pathway. So to start with the text itself. So our training data set, I think I mentioned, is about 10 million video clips spread across 5 million sites. I believe it's about 7 million of those, a little over 7 million, have text associated with them. So a big chunk of it. And how do we do that? It's not just the geocoded Wikipedia locations. It's also taking a subset of the GBIF observations with some filtering. It's all described in the, if you haven't read the supplement in the paper, if you scroll past the references, a lot of the data details are in the kind of back matter. But we've taken those species observations, and say you have an observation of a beaver, you've got Castor canadensis. We then link to the Wikipedia page text for beaver, and that will hopefully give us some understanding of, at this location, we saw a beaver, there was also wetland habitat and all the other things that are in the Wikipedia article about where that species likes to live. So it gives us that environmental context. That is a separate pathway in the model itself. So the model is generating that core set of Earth observation embeddings, what I showed you in the big model diagram. But the embedding coming out of that Earth observation piece also has to go through this other pathway pathway where it gets the text embedding, which is frozen. We've generated those at the start of the process. Those are just encoding that whole Wikipedia article into another condensed representation. And the model has a loss where it's actually being asked to pull those two closer together, which we believe helps encode some of that ecological meaning. Now, if you take a look at the ablations in the paper, they're covered a bit in one of the front matter figures and then in more depth in the supplement. We actually did the test where we took away different sensors. So we took away the text, we tried removing environmental context and removing the LiDAR and radar sources and looking at the differences. The difference in adding text was just a small bump. It's not like a huge leap in performance, but we really thought this was an important first step to understanding how you could incorporate text into this sort of model with the sort of data we had available. Again, not this like groundbreaking, oh my gosh, it was so much of a jump, but it did result in a performance improvement. We do think that it helps with that semantic meaning, aside from just the kind of per pixel semantics that we're getting from the semantic rasters that go directly into the EO training part of things. And so yeah, I hope that hope that answers. But yeah, it's definitely a unique attribute of the model, and we're very excited to understand what it contributes to.
Great, thanks, Valerie. We are short of time, but I will just take some questions which are like, can we use these models for other deep learning based tasks such as supervised classification tasks? I think the tutorials are available online. So on your behalf, I'm just recommending people to go through and check those. There is a common question which is like what to do with the higher scale resolution. If I want to work on 5 meters or 30 meter, what kind of sampling method would be used? And assuming traditional sampling method won't be applicable here.
Yeah, I will say really quick on applications of deep learning, my recommendation is we tried to optimize that simple, like start simple. So like, yes, you can absolutely use a big CNN, and if you've got the data to train it, by all means, go ahead and try it on top of embeddings instead of your usual features. But if you're starting from scratch, instead of reaching for the most complicated model, I would recommend anyone, start with those simpler, standard, classic ML techniques, because the embedding space is designed to work well with clustering and tree-based classification. So hopefully you don't need to pull out those really big, heavy classifiers. For higher resolution, now, we haven't tested a lot of this directly ourselves. My usual recommendation is kind of two different approaches. If you treat the embeddings just like any feature vector, you can tack on additional features. So go ahead and do your bilinear downsampling to your target resolution, get them down to 5 meters instead of 10 or 1 meter, and then add them as additional context onto your feature vector. So you can basically like take the embedding and use that broader pixel, tack on to the end of each of the higher resolution pixels. And now you've got a feature space that includes that finer scale and some of the embedding space information. There's also the possibility where you separate what you're trying to do in high resolution with what you want to do with the embeddings. And building type is a good example of this. Imagine you use a high-res model to actually segment out building objects or tree objects. Then go use the embeddings, which have so much richer measurement and temporal and kind of broader spatial context, and then classify the objects that come out of something high-res with the embedding features. So kind of a two-step process there where you might pre-process something high-res and then do a secondary classification of type for those objects using the embedding space. And I think that's a nice way to synergize without having to do kind of everything at that very fine scale. But it'll depend on the use case. And again, very excited to see what folks come up with. Everyone's so creative and how they combine different workflows and models and imagery that I'm sure we'll see more research in this in the coming months as people work on different applications.
That's great, Valerie. We couldn't take all the questions, but I'll recommend everyone to reach out to the team for any doubts or any requests they have or any questions they have. Thank you again for a super energetic presentation and answering all the questions. Maybe we can wrap it up for the day, and we would just like to know what are the future steps for AlphaEarth Foundations and the dataset. What are your plans going forward with that?
I think I've already shared, but yeah, we're making it more broadly available on GCS. We're registering interest on subannual time periods, and we're very much tracking all of the amazing research that folks are doing, publishing on. If you cite the paper, we get to see it on our Scholar Alerts. So yeah, we are just very excited to see what people are going to do and how this makes an improvement in all sorts of amazing application areas.
Awesome. Thank you very much again for joining. I'll also like to thank Sarah and Jerika for all their help in coordinating the event. And yeah, everybody, please uh, reach out to the team for more questions. And thanks again for your time. We'll meet again soon in another webinar. Thanks, Valerie.
Thanks so much.